patterns, gain, things like that. And I'll send it out to everybody by email, and I'll also post it on OneNote, okay? Everybody, okay with that? All right, thank you. All right, back to this problem. And this is a good problem, so I pay attention to this. Hint, I would pay attention to this. I hope you can follow me from that point on. All right, they want the S-parameter matrix for this, basically, for starters. So the key thing is finding the impedance of that capacitor. The frequency is 1 gigahertz. It means this impedance right here is going to be 1 over J times 2 pi times 10 to the 9th, right? Times C, which is 2 picofarads. 2 times 10 to the minus 12. So if you can give me that, it'll be minus J something. I don't know what it is. Minus J 29 maybe? Maybe it's minus J 30. I can't tell you. Anybody? No? Anybody look at this problem? This is a straightforward problem. Minus J 80? Okay. Minus J 80. All right, this is the first one we've done without the resistance in there. This is a capacitor. So, first question, is it lossless? Anyone?
Yes.
Why?
No resistance.
There's no resistance, right? It's stuck between the lines. It's a capacitor. It is lossless. Now, the next thing we need to do is find out. We're going to go ahead and get. I'm assuming it's matched, and I think it is, right? Match condition over there. If it's just stuck in a T line, it's assumed matched unless stated otherwise. So the first thing I'm going to do is get the reflection coefficient right there. And what does the circuit look like? Well, from this side, it looks like what? It looks like I have an impedance here of minus J80, and then I have a resistance here, or you could say a match condition of 50 ohms. And now I'm looking for reflection coefficient there. I came from 50 ohm 50 ohm transmission line. So what is that? Well, that's going to be the impedance I'm going into, right? Which is 50 minus J80 minus the impedance I came from 50 over the sum of the two of them over really 100 minus J80. So can you tell me what that is? I'm asking you to just do the problem so you'll know how to do something like this if it appears again on a quiz. This isn't a hard problem. It really isn't. Just know how to use the calculators and you won't mess it up. Give me magnitude and angle if you don't mind. You have to know how to use your calculators.
0.625 angle 51.
Say that again.
0.625 angle 51 degrees.
Angle of 51 degrees? Anybody confirm that? Okay. I'm believing you. Right? Now, that is S11, isn't it? By definition, that's in a matched, this is a matched load, so there could be no reflected signal coming in there, so that is V1 minus over V1 plus, and that's S11. You all agree?
I think we got minus 51.
Minus. Thank you. All right. Really, the 50s here, the 50 there cancel, so it's minus 80J. It should be a minus sign, just looking at that. Okay, now we've got that, and the minus sign is important. That's S11. Can anybody tell me what S22 is just by observation?
Minus 0.
Isn't it S11 the same as S22 because it's a reciprocal network? Doesn't that network look the same forward and back, class? Y'all hear me on this one? So you don't even need to do a calculation on S22. This is S22. Now, y'all agree with this, first of all. Okay, now, next thing I need to do is find S12, and how many, or S21 I should say, and how many realize that will be S12? Everybody follow me on this? It's a reciprocal network. So to get S21, that's equal to V2 minus over V1 plus, assuming V2 plus is equal to 0, it's just matched. It is matched. If there's a 50 ohm load here, nothing's coming back and reflecting into that second floor. Do y'all follow me on this, everyone? In the back, can you hear me and see me okay? I was worried about the guys in the back. Okay, so how do we do that? Well, the first thing we need to do, if we have, this is port 1, if we have V1 plus coming in, I need to find the value of what I call V prime there, correct? And V prime is the transmission coefficient times V1 plus. Do y'all follow me? The transmission coefficient is 1 plus the reflection coefficient times V1 plus. So I'm just going to put it here. So this is going to be I'll do it this way. It's a transmission coefficient, which is 1 plus the reflection coefficient, which is right there, times V1 plus, right? And then we have to find the voltage division that occurs. Now that would be the voltage right here. Y'all follow? Understand? That's the voltage just on the other side of the transmission line. Now I have to find the amount of voltage developed there. That would be on port 2 and it's leaving port 2. Y'all follow me? That's just going to be simple voltage division. Isn't that right? So what I'm going to say is I'm going to take that, and I'm not even going to put the V plus because it's going to go away. And it's just going to be 50 over 50 minus J80. I don't know what this is, but this should be pretty easy to see. So I'm going to have 1 plus 0.625 at an angle of minus 51 degrees. And then it's times 50 over 50 minus J80. I'm going to make a comment here when you give me that value. That would be, give me magnitude and angle. Most of the times, mistakes are made because people aren't familiar with complex numbers in their calculator. They don't know how to enter a polar number with an angle, or they have a hard time in the time they have allowed to do this kind of a calculation. It is not a hard calculation. You should, at this point in your careers, you should be very good at complex math with this. But I'm warning you, I know, I've seen trouble with this, lots of trouble. Okay, anybody?
0.781 at an angle of 38.66 degrees.
At say that again,
38.66.
38.66 degrees. Anybody second that? Close. All right. Now, if you didn't get it, take some time and figure out where you're messing up in your calculator. This shouldn't be a tough one. I'm just telling you that, but it is for some reason. I know because you remember the input impedance to waveguides? Remember that? That calculation drives people nuts a lot of times, that input impedance, and this one does too, these type of calculations. There's a lot of reasons for it, yeah.
Where did you get the 50 over 50 minus J80 again?
All right, if you look at this, now think, we're right here, we've got the transmission coefficients times V1 is there. Now I have to find out what V2 minus is, right? So that, if you look at this, it's simply voltage division, right? That's V2 minus leaving. So it's going to be 50 over 50 minus J80, voltage division. Y'all need, can y'all follow me on that? This is not hard, but I tell you, that complex number, this especially drives some people nuts. They don't know how to put in their calculator right. And you got to make sure you're working in either degrees or radians correctly, whichever one. Okay, now that is S12, isn't it? S12 is S21, correct? Because of the arguments of symmetry, it's reciprocal network. Does that agree with the book's answer? Anybody tell me?
2.2.
It's correct? All right, then what do they ask for after that?
Return loss insertion
All
loss.
right, this is just, you can forget about the angle, just take the magnitude, right? So what is return loss? It's minus 20 times log, that's base 10 log of the magnitude, in this case of the reflection coefficient of S11, correct? Because there is no ricochet coming out port 2. So it's just the magnitude of the reflection coefficient. Return loss, either way, is going to be the same. What is that? Can you just take the magnitude 0.625, take the log of that, and put minus 20 in front of it?
4.08 decibels.
Anybody confirm that 4.08? 4.08 dB. Y'all follow me. It's that simple, but you got to take a magnitude. Don't take a real imaginary part. Take the log of that. I have people doing that all the time. It's the magnitude. That's the return loss. What is the insertion loss? Well, it's going to be the same. It doesn't matter if you're coming from port 2, looking at the gain from port 2 to port 1, or the gain from port 1 to port 2. Because of symmetry, it's the same. So it's going to be minus 20 times the log of the magnitude of what? S21 or S12 in this case. And what is that? Just for completeness, this is a good problem. I'm glad you did it. I didn't do any with, complex numbers, I don't think.
2.14.
3.14?
2.14.
2.14. 2.14 dB. Anybody confirm that?
Yes.
Okay. That is, in essence, it's a problem that shows you how you deal with complex numbers. I mean, really, with impedances that are not strictly resistance, but that should answer your question. And there's nothing tricky, but you have to make sure that you get the reflection coefficients of those ports correctly, and that you get the voltage, I'll call it the transmission coefficient correctly. Because what people do all the time on these, they assume V1 plus here is that. It's not, right? Because it's a transmission line. Some of the incoming wave is reflected, and only the transmitted part is the thing that counts. Okay? Another question. Thank you. And if you did the problems, most of the stuff, I think we really did all the theory for everything. I mean, I didn't cover a 4-port network, but that's a simple extension of the 3-port networks. I want to talk, I mean, is there any other questions before I move on? I don't want to leave you high and dry. Okay. So now, can somebody send me a message to send a project? Just so, I've got a bunch of little things coming up right after this class, and I just don't want to forget to do that. Okay.
I got it.
All right, thank you. All right, we covered the resistive network, right? Where we had the simple divider that's based on resistors. Y'all follow me on that one, class? If you're looking in your booklets on page 570 on the bottom, that's just a simple splitter using resistors. Now, the reason that's nice is it's not frequency dependent. You hear me on that? So it's wideband. It does lose power though. You're gonna, if we could do the power calculation, you're gonna lose 1/2 of the power you put into that network, just burned up by heating those resistors. So that's not a good thing, but that's the way the splitters at your house, they have this. Now, if you wanted a more efficient splitter, something that loses less power, and to be frank about it, is probably more widely used for a lot of high-speed communication work, but I can't actually say that for sure. It's called a Wilkinson's divider. Now this is a very well-known one, and this is on page 571. So if you look at a Wilkinson's divider, here's this. You come in with a transmission line, and it has a characteristic impedance. We'll just call it Z0. Now this is still a power divider. Now you're going to have a piece of waveguide here and a piece of waveguide, or I should say transmission line this way. And, well, actually that won't work. Let me do it the better way. I'm just going to show one of these. So, this is going to have a characteristic impedance of Z0. This is going to have a characteristic impedance of square root of 2 times Z0. This is going to have a characteristic impedance of square root of 2 Z0. And the length of these things right here is going to be a quarter wavelength. Now, he should show this. Now, he shows a whole transmission line thing, but this is on page 571. And then, coming out here, it just goes to the standard Z0. I didn't show you the way he does it, where he has the upper and lower portion of the transmission line. I'm just showing you, this is the characteristic impedance Z0. This is going to be the square root of 2 times Z0. This is the square root of 2 times Z0. Y'all follow me? And it's a quarter wavelength long. Now, anybody want to take a guess why he used a quarter wavelength there? Do you remember a quarter wavelength transform? By the way, there's one other thing too. There is actually resistance that's here that will be 2 times Z0. I think he he'll show you that resistor, sometimes they don't. Ideally, there'll be no current that flows there, I'm just telling you, ideally there won't be. And, they're both to the upper pin of those things, to the positive line. So when you have this, what do we know about quarter wave transformer? And I wanna make sure I bring this out. When you had a quarter wave transformer, you remember if I had something and it was a quarter wavelength, let me do it this way. So I knew that Zn for anything was Z naught, then it's times Z load plus J Z naught times the tangent of beta L over Z naught plus JZL tangent of beta L. That was the input impedance. So if we had something that was a quarter wavelength long, and this was Z naught right here, what would the impedance here be? And this is, or I'm sorry, that's Z naught, and this is Z low. Well, when you look at that, what would Zn be? Take a look. If it's a quarter wavelength long, the key thing is looking at this argument of beta L. Beta L would become beta is 2 pi over lambda, and if the length is a quarter wavelength, this is pi over 2, right? Please just watch this. Do y'all follow me? What's the tangent of pi over 2? What's the tangent of 90 degrees? What's the tangent of 0? 0, right? It goes up, it goes to infinity. Y'all follow me? Asymptotically approaching infinity. Now, follow me on this. If we know that this is approaching infinity at the same rate this is, these two terms right here don't matter, do they? Y'all follow me? Neither does that. And what do you see happening? That doesn't matter. So I get what? Z naught squared over ZL, right? Right? Z naught squared over ZL. Okay? Now, what is ZL here? Forget this for now. That shouldn't matter. It's Z naught, isn't it? All right. So now I have Z naught squared over Z naught, or Z naught. Over there I have Z naught. It's in parallel with this one. And the whole idea is this. That Z naught there, all right, is equal to this 2Z naught, square root 2Z naught. Y'all follow me? Well, I didn't do this very well, but I should have basically said that this characteristic impedance is the characteristic impedance of the transmission line, all right? All right, that characteristic impedance of the transmission line is actually square root 2Z naught for this quarter wave portion, and the load is Z naught. So really, you're going to have square root 2. If you look at this, just hold on, I'm not saying this very well. Let me redo this because I feel bad. I'll make this point. What I'm going to do is call this, instead of square root of 2Z naught, I'm just going to call that, I'll call that Z naught, and I'll call this ZL here. And call that Z naught here, and this ZL. I think you'll see it, I hope you do. So my input impedance, Zn, you know, is Z naught, that is the Z naught there, times ZL plus J Z naught tangent of beta L over Z naught plus J ZL tangent of beta L. I want to make sure I say this correctly, because you won't see it if I don't. If I take a look at this, if it is a quarter wavelength long, then these two terms don't matter, that J doesn't matter, and I get Z naught squared over ZL, and that's Zn. This is for a quarter wave transform. Do y'all follow me on that? I'm just trying to make it clear. This is for a quarter wave long section, where ZL would be the load, and Z naught would be the characteristic impedance. Now, follow me. The characteristic impedance here is actually square root of 2Z naught. Y'all follow me? Look at the Wilkinson's divider. This one's going to be square root of 2Z naught, square root of 2Z naught. Just for this quarter wave section. So when I come over here and I put square root of 2 Z naught squared divided by ZL, and ZL is Z naught because it's going into a match condition. then I get what? I get 2 Z naught. Y'all follow me on that? Now, why is that important? Because if I'm looking this way and I see 2 Z naught, it's in parallel with this, which is 2 Z naught, which means the parallel sum is Z naught. Y'all follow me? And that means the reflection coefficient here is actually 0, and that's what you want. It's matched. Now, here's the thing about this divider, and I'm just leveling. This is great. If you're at an exact frequency, it works. But remember, that quarter wavelength is quarter wavelength for only one frequency. So any kind of frequency spreading of significance, and this thing doesn't work worth a darn. That resistor right there is a long story on that resistor. There's 2 R naught in that. That basically is to cause any power problems when you're going to have loads out here that reflect back and stuff like this. Without getting into all the details, this thing will basically minimize the amount of reflection that gets back into the transmission line portion. But there's a whole lot to be said about this that I can't say here. Just realize this resistor, ideally you don't need that. It shouldn't matter. You don't need that. But it's there basically to prevent some reflected energy from getting back into the sending circuit. And there's all sorts of problems. See, these things, anytime you have stuff like this, ideally this right here is lossless, but it won't be ideally lossless if there's any mismatch at all. I mean, it'll be bad. It gets bad in a hurry with these things. So what are the S parameters? And he shows this on page 570. We could go through them, but I'm just going to show you this. The actual S parameters for a Wilkinson divider are minus J over the square root of 2. And it will not be over 2, but square root of 2. And then it's the same as the actual, what do you call it, the resistive divider. It's just 0, 1, 1, and then 1, 1, 0, 0, 0, 0, and everywhere else. And, oh, I'm sorry, not quite the same as the other one, but it's 0 everywhere else. This is the Wilkinson's divider, and this is the S parameters for it. It's shown in his book. You'll notice one thing about that when you look. That minus J thing right there, that's a 90-degree shift. And that's something to take there to actually observe here. The ideal thing is the reflection coefficients are all 0. That's the ideal, because you don't want any reflected energy. So it's not perfect, but it's better, a lot better than the actual resistor divider. I'm going to mention something about 4-port circuits. And you can have any number of ports. 3- and 4-port circuits are usually used for telecommunication work and for radar work. And I'm not going to spend too much time on this. Do you remember how we had a circulator and we had some power going into one port and launched, and anything coming back through that port was redirected to another port, right? That's the most common thing you see with radar. But radar they will use circuits where they have 4 ports. I don't want to spend a whole lot of time on this, but 4-port networks have to do with, if you have a microwave system, I'm just going to try to make sense of this. Anytime you have any signal where there's a lot of synchronization needed, I mean, with radar, you have to have an exact known portion of a known signal that you're sending that you can actually use to do a lot of stuff with. Basically, you're going to sample that, do an A to D, you're going to store it, and you'll have exact timestamps when it was sent, because when the stuff comes back, you're going to use that information, have very fast correlators, match filters, take a look at the output quickly. And it becomes very important to precisely know something's dripping up there. I just saw a drop of water. Okay. Anyway, I just wanted to make sure you didn't catch one of that. Anyway, so what they'll normally do is they'll have the main signal and the through signal. And this is nothing more than it's going to let it go through. Then it will take maybe 20 or 30 dB off that and redirect it for some other reason. Synchronization, storing, whatever. Then they'll have one last port. And that thing usually doesn't do a thing, but sometimes they'll have like 70 dB loss, and they'll use that as a secondary signal, a very low level signal they're going to use for something else. But it basically is something where they're bleeding off the signal strength. I mean, they're reducing the signal strength and the loss just so they can catalog information, that's it. Has nothing to do with anything like a circulator. But that's really a 4-point in a nutshell, and I'm not even gonna cover that today, on that one. Now, I wanna tell you this much, I'm going to go ahead, on Monday, and, we have 1 week before Thanksgiving, I'll send out your project, I'll go through some of the filters, I'll do a little more of a 4-port that's more appropriate for this class, I don't have time today to do it. And then, if we have time, we're gonna go back through, how many have had the bounce diagram when you did transmission lines? Who did you have for that? Okay, you had me, you had it. How many have not had bounce diagrams? You know what I'm talking about? You've had, alright, so I found out that some of the other professors didn't teach that, it's actually real important. I'm gonna go over that again, on Monday and Wednesday. And now, you're getting your quiz early today. So, alright, everything off your desk except, calculator.
Telephone suspended. The controls. That's it. Middle school. I just that's the way to do it.
Give him one behind you, okay? When you get.
Somebody's right here.
Huh?
Like, he's put it back.
Alright.